Who would like to go first? I don't have any particular order necessary for today. All right, I'll nominate. Lars, would you like to talk first?
Yes, I can do that. So I have to make a short spiel about let me share some screen here. About the product we got for making Dave4VM available for Python and the SunPy community. Yeah, okay, you see my screen. So we got the project. We even got selected and got money, so we're pretty happy with that. And the project is to make Dave4VM, that is differential affiliated velocity estimator for vector materials with Doppler rosters into the SunPy system. I'm the PI of this. My name is Lars Daldorf. This is work together with Pete Chuck and collaborating with Will Barnes on the SunPy side. And this work is basically based on a bunch of paper by Pete Chuck, you can see upper left, and also some work recently by a PhD student at Hawaii that just defended Jerry Liu. So what do Dave4VM do? It tracks vector metrograms with magnetic induction equations to get the plasma flows. And that is supported by additional observation of Doppler velocities to get the normal velocities better as measured than in the code. The goal is to integrate the existing Fortran 2018 plus IDL code with Python NumPy in NumPy. So we get it into Python, and after that is done, we will integrate it with the SunPy ecosystem. So basically can flawlessly get to vector other data from SunPy. You can then pass them straight the same object into PyDave4VM and thereby getting the result, including all the metadata that follows the data set. So that is the core of this project. But there are all the alternatives on the field already. So, but the three categories, there's the feature tracking, like correlation tracking, Fourier correlation tracking, and machine learning methods, and it is solving the adduction equation. And for solving the adduction equation, there's only one other alternative, that is a PTD Doppler FLCT or PDFI code. But we have some different approaches to how we are treating the data. So we have some discrepancies there. They can look into Jerry Lee's latest paper in prep, where they talk about that extensively. But with this package, we hope to get all this available to the community to make it easier to use plasma flows and evaluating systems for energy release in active regions, things like that. So the timeline of this, our hope is to get something out before Shine or SPD next year, and then have some kind of mini workshop there presenting the package to the community, also try to get some feedback on which features they want and how to best proceed with the project after that. And this is a 1 year project, 0.2 FTEs, and it will end 1st September next year. So that is a short overview of the project. If you have any questions, please come.
Thanks, Lars. Do you have a comment or question?
Quick question. Is Dave4VM WD available openly already, or?
Not with Doppler velocities. It's going through the release process at NASA, so we're working on that. There is part of the code that is available, so we can give you, but there's not an open source license as yet, and that is one part of this process to get that. But it is a fully, also without Python, it is a fully working system at this time, but it's based on IDL and Fortran.
Okay, thanks.
Great. Nick, since you already unmuted, would you like to go next?
I figured that was coming. As long as I can share my screen. Oh, I need Lars to stop sharing. All right. And hopefully this does not crash Zoom.
Yep,
Ah,
see it.
is it showing? Okay.
Yeah.
And it's full screen?
Now it is.
Okay, cool. Yeah, glad that Zoom didn't crash while I was sharing my screen. It's happened sometimes lately since I did an operating system update. So I'm going to give an overview of the NASA HTM award that for maintenance for Plasma Pi, and I put the proposal itself on Zenodo. So if you want to go take a look at it, please feel free to. If you look up the Plasma Pi community on Zenodo, you can find that again. All right. So my one slide overview of Plasma Pi is an open source project, and its mission is to grow an open source software ecosystem for plasma research and education. If you want to learn more, please feel free to go to the documentation. So to give an overview of the funding status for Plasma Pi, we've had an NSF Cyber Infrastructure for Sustained Scientific Innovation Award that is ending in, I calculated it to be about 8.6 days. And we submitted a renewal proposal, but though it was ranked in the highest category, it was declined, unfortunately. So we're planning to resubmit the Monday after Thanksgiving is when it's due again. So the NASA HTM award arrived just in time, and it's focusing on Plasma Pi infrastructure maintenance for 3 years. So there are a lot of tasks that we have in the proposal for running Plasma Pi. So do things like coordinate code development. So we have fortnightly, biweekly community meetings, and we do this like for most PyHC projects through GitHub issues and projects. Also includes doing code reviews for contributions from members of the broader plasma and heliophysics communities. And the stretch goal is if I have time, then I've considered creating like a development roadmap or going through a road mapping exercise. And that would involve getting input from the community. So for project maintenance or package maintenance, Zed will perform about 3 releases per year to the Python package index PyPI. We also want to make sure that Plasma Pi has maintains and improves interoperability with other packages in the Helio Pythoniverse. And this includes the PyHC environment that Sean has been shepherding for the past few years that gets used in the summer schools. And then implementing approved PyHC enhancement proposals. And then work on the package infrastructure itself. So some of the tasks include maintaining the continuous integration CI infrastructure. And most of what Plasma Pi CI is Nox sessions that are invoked by GitHub workflows. And Nox is a task runner, a lot like Tox, if you're familiar with it. But the configuration files are written in Python, and I found it to be significantly more user-friendly than Tox. And then things like test coverage, and then linters and auto formatters and all sorts of other hooks and pre-commits in pre-commit. This also involves fixing new CI failures. And it's an unfortunate truth that upstream releases occasionally break CI. If you leave software in isolation, it's going to slowly become outdated just because of changes in the surrounding ecosystem. We have a system where we pin our requirements that get used in CI using uv.lock. And we have a weekly pull request that updates the lock file. When that pull request is submitted, the CI gets run, and we can find out if there are any new test failures or documentation failures or anything like that. And it lets us fix the failures before they get used in CI for other pull requests. So this greatly reduces the times where a contributor comes in and, oh, there is a new CI failure that has nothing to do with their pull request. So this lets us fix things before they get used in CI. And of course, we also want to keep documentation builds working. As we all know, Sphinx releases bring joy and happiness to all, and they never have any breaking changes whatsoever. That is slightly a lie. But keeping Sphinx up to date and the Sphinx extensions that we use up to date helps. It'll also be important to sustain the Plasma Pi community. And this includes things like providing user contributor support, and when possible, do this via documentation update. So if someone asks a question, help them and then update the documentation accordingly. I'm also going to provide tutorials, so including at the PyHC summer school, I'll get to go this year and in 3 years. And then there's a Suli intro course. Suli is the summer undergraduate leadership initiative, something like that. It's a program run by the Princeton Plasma Physics Laboratory, and they have an Intro to Plasma and Fusion summer course. And we've done tutorials for Plasma Pi for since early in the pandemic. We also want to update the contributor guide. We have an extensive contributor guide, making sure that it stays up to date and covers everything that it needs to, and doesn't cover anything that it doesn't need to, can really help with onboarding new contributors, which is the last task there. We're also going to expand the usage of type hint annotations. And if you're not familiar with them, they're the things where you say what types are expected and for attributes, or for arguments to functions, and then the return values. And by default, these do nothing. For Plasma Pi, we use them occasionally to make sure that things have the right units and whatnot. We use MyPy to check that these type hint annotations are correct, or at the very least consistent. Using MyPy has been kind of clunky, and it's not the static type checker that I would recommend these years. And so I'm considering switching us from MyPy to TY, which is a new static type checker by Astral, the makers of UV and Rough, which is not ready for production, or based Pyrite, which has a lot of really nice features also. So final thoughts. I'm really grateful for the HTM Maintenance Award because it's going to help make sure that Plasma Pi stays sustainable for a bit longer, next few years. And I'm happy to work with you to improve interoperability between Plasma Pi and other PyHC packages using a phrase from the proposal as time permits. All right, that's it.
Thanks, Nick. Any comments, thoughts, questions from the crowd?
All right.
Great. Thank you again. And I'm very, very glad to see one of our big resources in the community stay funded. Congratulations. Our last up for today, I believe, David, you're the one going to be presenting?
Yeah.
Great. Feel free to go ahead and share your slides if you have any, or just start chatting.
Okay, can you see the presentation in the full screen?
Yes.
Okay, so hi everyone, I'm David Anayan, third-year PhD student at UT Dallas. I'm presenting our GCM proposal for Python toolkit for the next generation of electron precipitation model. Just short science introduction for what's going on. We aim to extend energy range of energetic particle detectors data from Elfin spacecraft. They were 2 CubeSats at lower of polar orbit with energies just above 60 kiloelectron volts, and this energy range provides us very good data for looking at wave particle interactions and everything going on in radiation belts and in the magnetotail. But if we want to connect this data to ionosphere, so look at magnetosphere ionosphere coupling, turns out we actually need data slightly below that energy range. So the question arises whether we can overcome this energy limitation of Elfin particle detectors. Our suggestion is that yes, we can, using models. So here we try to use Salvation Prime model. It's a statistical model based on DMSP spacecraft data. So it can predict using Omni inputs data, electron number and energy precipitating fluxes in the energy range just below what is available at Elfin. It's written in ideal. Elfin data is mostly available in PySpeedus, so we want to try to use this ideal model to somehow create additional dataset for Elfin data. So we separate this project into 2 parts. First part is actually creating this Python toolkit separately from PySpeedus that will allow us to extend this energy range of precipitating electron fluxes. So assuming we provide this code, yeah, I'm sorry for this very rough flowchart on the left, but assuming we provide some Elfin precipitation number fluxes with timestamps to Salvation Prime model to get Salvation Prime results in terms of this magnetic local time and latitudes location. We can use a CGM module to project the Salvation Prime data to the location of the Elfin spacecraft. It's presented on the panel to the right. This white dot moving through the Salvation Prime data. And then, since we have this number and energy fluxes, we can try to reconstruct using some theoretical model this distribution of precipitating energy fluxes at lower ranges. So it's just nonlinear least squares fit to Elfin data for this parameter kappa, and other 2 parameters are just connected through some equations that we can solve numerically. And ideally, this should be exported as CDF files that we later plan to upload to Elfin data service. And it's actually the second step. Second step would be to using this toolkit that we plan to be publicly available on the GitHub repository, plan to apply it to all Elfin data to create a new data set and update the PySpeedus subroutines for loading Elfin data to actually have access to this dataset through PySpeedus. And here on the left is just example of what we can access from PySpeedus right now. This is the first 2 panels, and the next 2 panels is just this additional Salvation Prime model data that we plan to everyone to have access to. And ideally, this Python toolkit will work for any lot of CubeSat that will have similar energy particle detectors, as long as it has some geographic location and the user can provide Salvation Prime data. So that's it.
Wonderful. Any questions for David?
Not a question, more of a comment. This looks really interesting, and we'll look forward to having these capabilities added to PySpeedus, and for sure, let us know if you need any help or support with that. Looks great.
Thank you. So for now, we're just considering of releasing Python toolkit separately from PySpeedus because I don't know how, like, let's say, reliably it can be applied to other data and whether it is necessary to apply it to PySpeedus directly since the data for Elfin will be available through PySpeedus. But regarding loading routines, thank you. Yes.
Awesome. Any other thoughts or comments? Great. Well, thanks again for presenting, David. All right. Unless anyone has any burning topics in their pocket, we can call today an early wrap, which I'm sure no one is upset about a meeting ending early for once. A note that we will have an off-cycle telecon this coming Monday. It's some more HSSI, for those that don't know the acronym, Heliophysics Software Search Interface work. So get ready, and I'll see you all then.